Right, so today I will talk about the overview of the MOSFET. So the MOSFET, or we still call it as the metal oxide semiconductor field transistor, is actually operate on the principles of the field effect modulation, where a voltage is applied to a gate terminal control to flow of current through the semiconductor, and it is different to the bipolar junction transistor because it is a voltage control switching mechanism. And this is the structure of the MOSFET, which is a four-terminal collaborator to precisely control how the current flow. You can see there's a sources and there's a drain, and between the source and the drain, we're having the gate. And below the three of them is actually the substrate, and that is the semiconductor body. So this is the device, the type of the MOSFET. We're having the NMOS, which is an N type, and we're having the PMOS as well, which is a P channel, N channel and P channel. So the body or the substrate, we actually dope with the P type, and for the PMOS, we actually dope with the N type. And for the sources, which is the S part here, is actually having the donors, and for the PMOS having the acceptors. And here are the difference between the NMOS and the PMOS. So how the gates control? What is physics behind them? So it's actually a few physics principle. So how is it possible? It's actually that the voltage on the gate create a conductive channel from nothing. How do we going to understand this? Is we have to look at the vertical cross section of the device, which has shown in the diagram here. So the MOSFET structure is from a capacitor where the gate voltage modulate or alternate the energy band at the silicon surface. It create another energy band and dictating the presence of the type of the charge carrier. And the voltage can be calculated by using this equation. This is called as the flat band voltage. It is the gate potential required to counteract built-in field from the work function and the fixed offset charge, establish the electrostatic starting point. So this is the type of the voltage situation you will see. The first is about the accumulation, and we also have the depletion. We're having a strong inversion as well. And the difference is between the gate voltage and also the flat voltage. For accumulation, the VGS is less than the VFB. And for depletion, the VGS is actually in between the VFB and also the VTH, which is a threshold voltage. And for the strong inversion, obviously, it must be greater than VTH. That's why it's so called as the strong inversion. The gate voltage is greater than the threshold voltage. And at the time, because this is greater than the threshold, we so call it as on. The device itself is on right now. Okay, so the threshold voltage, what's actually the threshold voltage is? The threshold voltage is actually the precise gate potential required to create a channel, just like we have to greater than it so that we can create the channel to let the device on. And how do we going to calculate the VTH or the threshold voltage? By using this formula. We can using this formula to create the critical gate voltage, which it marks the transition to strong inversion as shown in the graph before. Now, threshold voltage is a dynamic parameter modulated by the circuit bias and temperature. It means it depends on temperature. It's not a fixed value. It could be changed, depends on how the temperature is. And also, it depends on the body itself as well. When the source voltage rises above the body voltage, which is the BS greater than the VB, it will become the reverse bias. And these will widen the depletion region, as we all know that in the PN junction. And this will making the increasing of the VTH, as right now the depletion region is greater. We need to overcome a more greater energy barrier. And that is for the left-hand side explanation. For the right-hand side, it's actually about the temperature dependency. So the MOSFET behavior range actually from an open switch to a control register to a current source. So this graph basically show off the cut-off region, the linear triode region, and also the saturation region. In saturation, the channel pinch off and transforming the device into a current source, as we often seen in the seen in the circuit. And the scaling imperative for a short channel effect that erode the gate control. As the length shrink, the channel effect could be enhanced. Sorry. Yes, and this is how the drain-induced barrier lowering and how is the velocity actually very important. Why velocity is important is that we have the high electric field and the carrier velocity will be accelerated, and it's actually saturated at the thermal limit as shown here because of the phonon scattering. It's about the lattice vibration, and this actually fundamentally limit how much the current can be pushed through the short channel, which means the maximum velocity of the charge carrier is actually be limited and it's not infinitely increased. All right, so it will not become ideal square law relationship anymore as the electric field strength increased and increased. And this is the FinFET realized the gate authority by wrapping the gate around the channel. So to combat the short channel effect, which we mentioned before, the industry actually transitioned the plano 2D to the FinFET 3D. This create the extra part that provide the superior electrostatic control by shielding the channel from the drain influence. It used to be source, drain, and gate. Now it having an extra part. So this is how the future scaling could be looks like. We having the gate all around we so called as the GAA. This is the same but it's an architectural evolution to increase the efficiency. And in this particular structure, the gate material is actually completely cycled or surrounded by the channel as you can see. This could actually achieving theoretical maximum of electrostatic control as it is now fully encircled. So this is the historical evolution view, and it might include the future as well as how the gate array could actually be preserving, and it's a MOSFET included as well from plano become an infinite FET and eventually become a fully encircled GAA. Thank you.